This presentation explains the ND2 NAND2 TRIAS project, which teaches how a computer is built from logic gates. The course starts from the NAND gate and gradually builds a complete working computer capable of running programs. It covers topics like digital logic, CPU design, memory system, and assembly language and computer architecture. Through this project, we understand how hardware and software interact inside a computer system. Boolean logic is a fundamental of all digital systems. Computer uses binary values 0 and 1 to represent all types of data. This value can also represent true, false, on, off, or high-low signal in electronic circuit. Inside hardware, transistors combine to form logic gates that perform logic operations. The Boolean function is a mathematical operation that takes binary input and produce a binary output. These functions are used to design logic circuits such as adder and multiplexer. By combining simple Boolean functions, we can build complex digital systems. They form a fundamental basis for all computer hardware operations. The first project focuses on building basic logic gates. Example includes AND, OR, NOT, and MUX. We also implement 16-bit version like AND 16 and OR 16, which operates on multiple bits simultaneously. This gate acts as a basic building blocks from which large circuits are constructed. The project provides HDL stub files with incomplete definitions. Our task is to complete the parts section to define how chips work internally, provided test script automatically check whether the chip work correctly. The output is compared with expected result to verify the correlations. The implementation is done using NAND2 TRIAS ID. The environment includes a hardware simulator that helps visualize circuit behavior. We can describe circuit using hardware description language. After implementing, we can run test script to verify the chip functionality. The theoretical basis include Boolean algebra, which explain logical operation mathematically. The NAND gate is a universal gate, meaning any logic function can be built using only NAND gates. Complex circuits are built through abstraction and composition of a smaller gate. SDL helps describe how hardware components are connected and interact. This project we implement arithmetic operations using logic gates. Binary numbers are processed using logic gates instead of traditional arithmetic operations. And this leads to building the arithmetic logical unit ALU. The ALU is the key component that allows the CPU to perform calculations. Several chips are implemented to perform arithmetic operations. The half adder adds 2 bits and produces a sum and carry. The full adder carry input for multiple bit addition. Add 16 and in 16 operates on 16-bit number. Finally, the ALU combine all the arithmetic and logical operation into one component. Binary addition is implemented using logic gates and carry propagations. Subtraction is performed using two complex representation. Multiplication can be implemented through the repeated addition and shifting. Division is typically done through repeated subtraction and bit multiplication. Computer represents single number using binary encoded system. The most common method is two complement representation. Modern computers follow von Neumann architecture where programs and data share the same memory. The ALU execution arithmetic and logical instruction provided by the CPU. The hacked ALU is the central computation component of hacked computer. It accepts two 16-bit input called X and Y. It produces a single 16-bit output representing the result of the operation. 6 control bits determine which operation the ALU performs. This operation include addition, subtraction, logical and or and other functions. Computer require memory to store data and provide instruction. RAM is originally the into addressable register, each storing a fixed number of bits. Each memory locates has a unique address used to access it. This structure allows efficient reading and writing of data during program execution. Earlier, circuits are combinational, meaning output depend only on one input. Sequential circuits also depend on previous state. They contain memory elements that store information over time. Sequential circuit logic is essential for register, counter, and RAM. This project introduced flip-flop, the smallest memory unit. Using flip-flop, we built register to store multiple bits. Counter can created to track sequential event. Combining register result in complete RAM memory system. This project introduced low-level programming directly with machine instruction. The programs are written in hack assembly language. These instructions are later converted into binary machine code. The program are executed using the CPU emulator. Students gain practical experience with machine learning programming. They learn the hack instruction set architecture. They also understand how assembly code is translated into machine instruction. This knowledge prepared them for building the hack computer. The NAND2 tries IDE, a development environment for coding and testing the assembly converted language code into binary machine code. The CPU emulator run the program and simulate processor behavior. Together, this tool create a complete learning environment for system development. Hack assembly language provide instruction to control program flow. Branching instruction allow conditional execution. Data movement instruction moves data between register and memory. Jump register change program execution path. Loop allow repeated execution of operations. In this, all the previously built components are integrated into a complete computer. The ALU, memory, and register are connected to form a CPU. Additional components manage instruction execution and control flow. The final system can execute machine learning programs. The hack computer follow von Neumann architecture. The CPU fetch instruction from memory using the program counter. If it then decodes the instruction to determine the operation. The ALU executes the operation and update registers. This cycle repeats continuously during the program execution. The assembler convert human readable assembly code into binary machine instruction. It reads the program and presses each instruction. A symbol table maps labels and variables to memory addresses. Finally, the assembly generates 16-bit code for execution. This project teaches how computers are built from basic logic gates. It demonstrates integration of hardware design and software programming. Students learn about CPU architecture, memory system, and assembly programming. It provides a complete understanding of how software interact with hardware. Thank you.